Hello, everyone. Good morning, good evening, good afternoon to everyone, wherever you are, and welcome to today's webinar. I'm your host today, as the usual. My name is Carmen Guguta. I'm your Global Head of Business Development and Marketing for Technobiz. And here today, I am with Christina Costa from Neurocrine. But before I start, I would like to share my screen. Just 1 second. I usually work with 2 screens, so and today I'm a bit more limited to 1 screen, and so do you see my screen, Christina? Oh. Sorry for this. You do here see my screen, right?
Yep.
Okay, perfect. Thank you. So today's webinar brought to you all by Christina Costa, Principal Engineer at Neurocrine Biosciences, investigating the relationship between void solvent and morphology via crystallization control. Before I go further with this, I would like to let you all know that this webinar is being recorded and is being made available to all of you later today or tomorrow morning. Will be available on our website. You will also receive an email related to the recording and the slides of this webinar where you can download them. If you have questions during the webinar, please use the question or the chat function of this platform and write to us. We will take the questions at the end, and we will try, both me and Christina, to answer all your questions. If you have questions later on after the webinar, please write to us to info@crystallizationsystems.com or later to Christina as well. We will share all the questions with her, so we will address everything, all the problems, issues, or questions that you might have. It will last about 30 to 45 minutes. And as I mentioned, we will address all the questions at the end. Now, just shortly, for those that do not know Technobiz Crystallization Systems, Technobiz, we are a company located in the north of the Netherlands. We're on the market since 2005 with more than 700 units sold worldwide. Since recently, we have 2 portfolios, one for crystallization, process development, and formulation, the Technobiz Crystallization Systems, and a second portfolio for reaction screening. This portfolio is the new one, the one that we have recently introduced with the instrument Reactor. This is exactly what I have mentioned to you, that we have these 2 portfolios on reaction screening and crystallization systems. On the crystallization product line, we have 3 instruments. I have seen some of you already are familiar with our Crystal 16, and some of you with our Crystalline or the Crystal Breeder. These are multiple reactor systems that you can heat and cool in a controlled manner. They come, all of them, with the transmissivity technology that allows you, when something appears, crystallizes in your experiment, in your solution, you can see it, or the same the other way around. When you have a clear solution, it can be detected. Crystal 16, remember, is your instrument for solubility, solubility determination, metastable zone width, induction time measurements, nucleation rate, phase diagram, polymorph screening, crystallization screening, salt co-crystallization, you name it. This is your instrument to go with 16 reactors in parallel. The Crystal Breeder is your instrument with 32 reactors working at microliter scale for growing single crystal. It comes, as I call it, with the gadget system, comes with a gadget for facilitating diverse type of crystallization methods, like, for example, vapor diffusion, controlled evaporation, and so on. And the Crystalline is coming with, besides the transmissivity technology, with cameras, microscopic cameras that allows you to see what's happening in the solution in your experiment. And additionally, with the software package and image analysis provided by this instrument, you can do particle size determination distribution, so the D10, D50, D90, you can measure shape assessment, and so on. So it's really your instrument for designing a crystallization process and optimization and formulation, of course. If you have a Raman spectrometer in your lab, you can easily connect it to this instrument and follow polymorphic transformations or even chemical reactions. So this was in short about the crystallization portfolio related to the screening, reaction screening. Oh, it went a bit too far. Reaction screening. Our newest instrument brought on the market just a few months back. The Reactol is the instrument multiple reactor system. I don't know why it's keeping on going. Multiple reactor system with automated sampling. Comes with the quench, dilute, and rinse here on the top, and the 5 reactors here. It's sampling directly into the HPLC vial. So you can literally, you see here the HPLC trays with the vials. You can directly put them in your HPLC and measure the concentration. Sorry for this. I don't know why I have this. It goes from one side to another one. So main applications for this instrument, the Reactol, are reaction screening, any type of reaction screening, optimization, reaction profiling and kinetics, route scouting. This is the instrument to go to. It really comes to fit in between the high throughput and low throughput, the gap that is existing on the market. This was about Technovis and our crystallization and reaction screening products. But here today, I would like to introduce our speaker, Christina Costa, Principal Engineer at Neurocrine Biosciences. Christina has a total of 10 years of experience, more than 4 patents in pharmaceutical drug development space. Her early career was spent working in small molecule pre-formulation contract lab sector, and after that she joined Neurocrine Biosciences, where she has been now for more than 80 years. She leads the material science department, supporting product development of small molecule and biologics projects through materials characterization, form screening, and crystallography. She got her bachelor degree in chemical engineering from UC San Diego and her master in material sciences and engineering from University of Virginia. Christina, thank you very much for helping us today and bringing this webinar for our customers, for our viewers. I will stop sharing, and I think I give the floor to you now. You can start sharing.
Great, thank you. All right, how's that look? Slides up.
Yes, I do see your slides. Perfect, you are good. Thank you.
All right. Thank you. Yeah, thank you everybody for joining me this morning, and thank you to Technovis for having me as well. I'm going to be discussing investigating the relationship between void solvent and morphology via crystallization control. So just a quick outline. I'll give a little bit of my own background, although Carmen already did a good job of doing that. I'll go through some brief theory, just really general background information on some basics of crystallography, nucleation and crystallization, and metastable zones, just to give us a good background and foundation to understand the case study that I'll discuss in the second half, which we'll call Compound X, which is a small molecule that has some interesting crystallization characteristics. I hope by the end of this talk, I can convince you all how important it is to characterize and have a lot history of the solid state characteristics of your compounds while you're moving through development, and also to show how crystallization and morphology can be very important and impact other processes, from your chemical process, analytical processes, and formulation processes. So just my background. My name is Christina. Carmen already mentioned, but I currently work at Neurocrine Biosciences, which is located in San Diego. I've been there for about 8 years, and I lead the material science group. So we are focused in solid state characterization, form screening, crystallization, optimization. Before that, I worked at a contract research organization called Pharmatech, which is now Catalent. And I also worked a little bit at Vertex here in San Diego. And I have my bachelor's in chemical engineering from UC San Diego and my master's in material science and engineering from the University of Virginia. All right, so here is our little bit of background information on crystallography. I'm going to be very general, so hopefully not going to bore everyone too much with a lot of complicated information. But if we're talking about crystals, we'll talk about them from a very basic understanding. So we have our molecule. And if we're forming a crystal, then those molecules are going to come together. They're going to bond. They're going to create some sort of symmetric repeating pattern that's going to have long range order. And as long as we have this, then we're going to have a crystal. If we look at our smallest unit of symmetry in that repeating symmetrical pattern that the molecules are forming, that is called our unit cell. And you can think of the unit cell sort of like a scaffolding, a building scaffolding, and we're kind of stamping onto these different lattice points within the lattice cell our molecule. And this unit cell then will continue to stack on top of each other as the crystal grows and form the macro structure, the structure that we're going to be able to see when you look at something like a gemstone or a mineral and you see the faces in it. All of that comes down to that basic unit cell structure and the symmetry that's within your crystal. And if we look at that unit cell a little bit more, because we have different lengths of our sides and different angles, all of that's kind of mathematically limited to only a certain amount of possibilities. And because of that, we have a known limited amount of crystal systems which crystals can exist in. And among those, we have 14 possible lattices. We won't go into too many details on any of this. I just kind of wanted to get in everybody's head that these are sort of the basic building blocks of what makes a crystal. And if you're thinking about polymorphism, for instance, polymorphism is just the ability for your molecule to form different crystal lattices from each other. So if you have polymorph 1 versus polymorph 2, they're going to have a different symmetry, a different long range order, and they're going to fall into one of these different systems. And then again, when we kind of expand that, we look at the macro version of what those unit cells are going to eventually build into. Each of these crystal systems sort of has a known habit of the crystal that you'll eventually see. Just for a very basic example, everybody should be aware of, if you think of sodium chloride, that is a face-centered cubic structure and a halide mineral. So you can sort of see the building blocks and how they eventually build up to create this macro crystal. So that's what a crystal is, but how do we form a crystal? And that's a discussion of nucleation and growth, which again can get very complicated and have a lot of crazy math involved, but we're going to think about it in a very basic way. So if we have one of these two systems, we might have a system that is a supersaturated solution that is clear, or we might have a supersaturated system where there are existing crystals of our molecule present. For example, if you were to add seeds to the solution. So these are what we call primary nucleation or secondary nucleation. And there's going to be different energies associated with what it takes to grow the crystal within these systems. With secondary nucleation, we already have sort of that scaffolding there, and our crystal can grow off of those seeds in a more controlled manner. Primary nucleation is going to be a stochastic or a random process And we can further break that down into two different situations. Either this is occurring in solution spontaneously, or it's occurring on a surface or an impurity. And that is what we call homogeneous nucleation or heterogeneous nucleation. So if we think of homogeneous nucleation, we have our molecule particles, they're floating around in this saturated solution. They're going to collide with each other. They're going to eventually sort of stick together and form this nucleus. And then if that nucleus gets a large enough volume, it's going to have enough energy to then solidify and start to crystallize and form our crystal. In the case of heterogeneous nucleation, we're going to have some sort of essentially starting point where our nucleation occurs. Either you have a crack in your vial or a piece of dust or something else, that's sort of a lower energy pocket that our nucleus can sort of stick to, form, and crystallize off of that. Now, all of these processes are random, as I mentioned, and whether or not they're going to happen is based on the free energy of the system. So those molecules will form a crystal lattice when the energy due to the volume that the nucleus is creating overcomes the energy required to form a surface. So all this is just to create sort of an understanding of how our crystals are going to grow and why it's important for us to understand the whether or not our crystal is going to grow and how to control the variables to ensure they're growing. And one way we can really understand that and plot that and have a good visual of our crystallization control is with a metastable zone width. So this image here is showing a metastable zone curve. You can see we have concentration on the y-axis and temperature on the right. And essentially what it's doing is defining different regions based on whatever concentration or temperature your system is at. So if we look at part A over there, where we have our A, that is in the stable undersaturated region where crystal growth is impossible. So you can think of this like you have a one set concentration of your sample and you're heating it up to a temperature past that dissolution line there. You can think of the dissolution line like your solubility line. And once we get to that temperature, we're able to dissolve the sample. We now have a clear sample. Then if we were to take that same sample and cool it down and follow the line all the way to B, we hit a point called the nucleation line or metastable limit, called a few other things. But if we continue past B into the region above that, we're now at a supersaturated region where crystallization is spontaneous. And so we're going to have our crystal start growing, precipitating out of our supersaturated solution. The region in the middle is what we call the metastable zone. It's going to be an unstable region where we're lowering our solubility essentially past the point where we were able to dissolve it. So we have this very supersaturated solution, and we're able to then introduce seeds, for instance, or we might have some sort of uncontrolled heterogeneous nucleation occurring in this region. So what this system does is really help us understand if we know our concentration and we're able to control our temperature, we should be able to control our crystallization. So how do we generate a metastable zone? We're going to use an instrument like a Crystal 16 from Technobis, and we're able to define this region through a few experiments. So we're using a temperature variation solubility, and we're going to have samples of known concentration that we're going to heat up, see when they dissolve, and then cool down and see when they crystallize. So if we look at this chart on the left, starting at the bottom, we're going to know and control our temperature, and then we're going to be recording our transmissivity. So assuming we have a cloudy suspension, we're going to have a 0% transmissivity, and then we're going to heat up. So you can see our temperature is increasing, and at a certain temperature, our vial is going to go clear, and all our crystals are going to dissolve, and we're going to have a clear solution. So our transmissivity goes up to 100%. So at that point, we call that the clear point, and the temperature that occurs is the clear point temperature. We're then going to lower our temperature until we get to the point that we start to have crystals in our solution. We're crystallizing, we're crashing out, we're precipitating, That point at which that happens is our cloud point, and it's at the cloud point temperature. And you can see it's pretty likely and pretty often that there's a gap in between that clear point temperature and that cloud point temperature. So that is a region in which we're cooling down and we're getting past the point of our normal solubility, and our solution is going to be super saturated, but the solute has not yet precipitated and crashed out. So that is what our metastable zone width is. And we're going to repeat this with multiple concentrations, and then we're able to plot those on a metastable zone width curve. So in the bottom right, you can see there all of our orange points are our clear points, and that creates our solubility line. And then the blue points are different concentrations reflecting cloud points, and that's our metastable limit. Okay, so our last part of the theory lesson is I just want to remind everybody that a lot of times when you're talking about crystals, we're assuming we're having perfect growth, we're going to have perfect symmetry, but that's usually not the case. Sometimes we're going to have defects and dislocations in our crystals. We might have vacancies in the lattice, we might have substitutional atoms in our lattice, and sort of impurities or other things that can be going wrong here. And that's going to cause strain and stress within our crystal lattice. And it's going to create growth and interrupt growth in different directions. So we might not have the exact perfect structure that we're expecting, but that's more than often the case. And it's not necessarily a bad thing, but it's good to understand when it's happening. And with that background info now out of the way, we will go on to our case study. So we're going to be discussing compound X, and here is some background information on that material. So if we're looking at the physical properties, it's a small molecule being developed as an active pharmaceutical ingredient. It's crystalline. It has a single true thermodynamic melt. It's anhydrous and unsolvated. It has no significant polymorphism, and it's chemically and physically stable as solids and as liquids, so or in a solution. From a solid state perspective, all these properties are very favorable. We look at some of the development properties. It's extremely soluble in pretty much every organic solvent. It is slightly soluble in water and heptane. We've seen some odd variable dissolution results where it seems like the dissolution is very kinetic and kind of hard to control or predict. It has a bit of a complicated crystallization procedure that takes several steps and requires seeding and requires a pretty long time for the crystals to grow. And we also have seen several lots that have solvent on them, usually a higher percentage that can be out of spec for analytical certificates of analysis. So we would call some of these challenges, and we want to better understand how we can better mitigate some of these challenges as this moves through development. So from very early on in this project, my team had been doing materials characterization on various lots of this material. And one thing we realized in the thermal analysis is that there was often a weight loss step that occurred with the melt. So this graph here is thermal data. This is differential scanning calorimetry in green and thermogravimetric analysis in blue. So if you look at the green curve, the DSC, we see that sharp endothermic event that is the melt of the material. And then in the blue curve, the TGA, you see the step that is lost with the melt. And because this, the percentage of this step varied from lot to lot, it happens at a pretty high temperature and it happens along with the melt. All of this led us to believe that it was likely this was not a stoichiometric solvate. And what I mean by that is the solvent molecule is probably not actually a normal part of the crystal lattice, but rather it's likely trapping solvent molecules within the voids of the lattice. We were able to get single crystal structural information as well that confirmed this polymorph form was unsolvated and that it did have voids in the packing of the structure that were large enough to trap molecules. So because we saw this as a variable amount, we made the team aware and made sure people knew that this lattice was likely to hold on to solvent this way, and we wanted to express to everybody that you cannot get rid of this with drying. If you heat this up to try to dry it, it's not going to get rid of the solvent. The only way to do that is to melt the crystal or break up the lattice in some way to let that void solvent escape. So we continued to keep an eye on this as it moved through development, and a little ways down the line, we saw some process familiarization samples from our chemical development coworkers, and they noticed 2 lots that macroscopically had a bit of variation in their morphology and powder properties. So we wanted to look at those a little bit further. So if we think macroscopically about the material on the left, it's sort of a fluffy powder. It has these large aggregates and clumps, and it's more white in color. The one on the right, if we were looking macroscopically, is a finer powder. It has some aggregates and clumps, but they're much smaller, and it has a slight yellow color to it. Well, when we looked microscopically with scanning electron microscopy, we saw that the material on the left had these long, flat, acicular needle-like particles. And we saw that the ones on the right had these shorter particles that were reticulated. They were kind of growing in these clusters and growing on top of each other. And they're not just loosely aggregated, they are fused and growing on top of each other. The interesting part of this was that both these are made with the same crystallization process. They are both seeded, which usually is a way to control the morphology. We confirmed both were the same polymorphic form, and we also looked at some of the thermal behavior and saw that they both had different amounts of that void solvent we had seen before. So once we saw this, my team was interested in it a little bit more, and we wanted to see if we were able to better understand if there's a relationship between that propensity to hold on to void solvent and this very different result in morphology. So we basically got our hands on as many lots as we could find and started analyzing them further. So this is an overlay of TGA data showing that weight loss event in the region of the melt for a bunch of different lots of this material. What you can see is how much it varies. So we have this weight loss step anywhere from almost nothing, 0.05%, all the way up to 1.4%. And I want to, again, highlight that none of this solvent is residual. It essentially loses no weight up to about 75%. All of this weight loss is occurring with the melt. So we then took all these lots and we did scanning electron microscopy on those. And this is what we saw. So starting from left to right, this is the least amount of void solvent on the left and the most amount on the right. And what you can see is a very clear trend in the change in morphology here. So starting with the least amount of void solvent, we have those long, flat needles, and then we start to get shorter in size, and they start to fuse together and start growing on top of each other. We start getting these radially divergent clusters of growth, and then we start seeing these very fused on top of each other, very short, stubby particles as we get to the right and get to the increased amount of void solvent. So after we saw this, we were definitely confident that there was a correlation between how much void solvent was in the lattice of these particles and what the eventual morphology would be. So because of that, we wanted to better understand how to control for one versus the other and just kind of understand what was happening and why this was occurring. And this is sort of just a little cartoon I made for a meeting where I was trying to explain sort of my hypothesis of what was going on. But if we think back to our discussion of nucleation and growth, this is sort of what could be happening here. So we start at the left, we have our supersaturated solution. We have API molecules and solvent molecules floating around in that supersaturated solution, and we're introducing a seed. So we introduce our seed and initiate nucleation. So the crystal starts to grow off of that seed. And then it seems like we have two kind of different paths. On the top, there's either this growth that favors the lengthwise growth and forms these needles. And in doing so, it's trapping very little to no solvent within the lattice. Or on the bottom, we have this growth that sort of starts to diverge due to strain because it is trapping so many of these solvent molecules within the lattice, and it's starting to grow off in different directions. So to help us understand how we can control for one versus the other, we utilize the Crystal 16. Sorry, Tech Novus, that we have the older one. So I just used a picture of the older Crystal 16. I know there's a pretty shiny new one. Well, this is the one we used for these experiments. And what we wanted to do was utilize this for different solvent systems, generate some of these metastable zone width curves, and see if we can control for these different morphologies. So our study design, what we were looking at is, first we wanted to look at solvent selection. So we wanted to know that if we chose certain solvents, whether or not it would be more or less likely to form the void, or to get trapped in these voids and form these different morphologies. We then wanted to look at the potential for binary mixtures with antisolvent so that we could have a single solvent system that we were utilizing in our cooling crystallization instead of having to do solvent swaps and seeding, which seems to be, in the case of this molecule, difficult to control the morphology. So if we're able to just have a single solvent system that we cool down and nucleate, we might be able to control the morphology better. We also wanted to understand whether or not the heating and cooling rates and whether or not we cool faster or slower inhibited or encouraged this void solvent formation. Starting off with solvent selection, as I mentioned before, it is extremely soluble in pretty much all solvents. So we had a hard time picking solvent systems to look at, but essentially what we wanted was to look a little bit of a variable size of the solvent molecule itself. So, excuse me, starting with something like IPA, which is a much smaller molecule, takes up less volume. We wanted to see if it was more likely to trap within the voids. And then something larger like dimethoxyethane, it's more of a longer chain. We wanted to see if maybe that would be less likely to be trapped. We then have water and heptane as two options, small and large, for our antisolvent. So then after many crystallization runs with few different mixtures, different concentrations, different amounts of antisolvent, we saw some general trends. So this is just highlighting overall what we saw from these results. So these are kind of listed from left to right, with the left being the largest volume solvent to the right, which with water being the smallest volume solvent. So on the left, the dimethoxyethane, almost all the experiments with this solvent resulted in very low amounts of void solvent trapped in the lattice, and they all resulted in the morphology with the long needles. We had a similar story with the isopropyl acetate, again, a larger solvent volume, which resulted in a lower amount of void solvent, and we again saw smaller thin needles. When we start to get into these smaller volume solvent systems like IPA and water, we then started to see more of those clusters forming, and we also saw variable and high amounts of void solvent, with the most being the systems with water. We typically saw almost over 1% for almost all of the samples with water, and we actually saw a new morphology with some of these water samples where instead of the needles, they were actually forming thin plates that were sticking into each other. So just to confirm that we definitely could control for this worst case example, sort of with the IPA and water, we did some more experiments with that. So this is a water IPA system that we recrystallized in. This graph here is TGA mass spec data. So in the blue, you see that weight loss event, that's the void solvent coming off. And then you see the overlaid with it, the mass spec data, which just confirms for us that this weight loss is water and IPA being removed from the system as the crystal melts. And all of those molecules were trapped within the lattice. And then on the right, you can see morphology, and you can see those long, thin plates and how they're fused together in almost a large clumps. And this was sort of our worst case example of the high void solvent and very clustered morphology. So then we wanted to look more at our binary ratio systems, see if we can control for the other morphology type, the needle-like particles. And so for that, we chose just the solvent systems with the larger volume. So ethyl acetate, isopropyl acetate, and dimethoxyethane. And then for antisolvent, we used heptane. These three graphs are just solubility. We wanted to try to narrow down what percentage of solvent to antisolvent to use. And what we found was it was actually pretty difficult to find in an ideal system. So the blue lines there, the blue points are room temperature solubility, and the orange points are heated solubility. So ideally, we want to have a low solubility at room temperature so that we're able to crash out a solution and have a good yield. We want to have a high solubility when we heat up so that it's easy to dissolve and we don't have to go too high in temperature to where we might be degrading something. So what we ideally would have is those two dotted lines, the blue and the orange. We want to have our solubility values be outside of that range. So for all of these systems, we essentially could not find that system, but we tried to pick the best cases that we could and run with those. And so those are circled here. In the case of ethyl acetate, we have the 50-55%, isopropyl acetate 75-80, the DME 45-50. So when we started doing more of our metastable zone with runs on the Crystal 16, what we found is the challenges didn't end there. We continued to see some pretty odd results. So this behavior we pretty much saw across the board. We saw in all of the different solvent systems, but I just have a few examples to sort of highlight what we did see. And this first example is just kind of showing how we had some difficulty finding that nucleation line and defining our metastable zone with for most of these systems. So what this graph here is essentially the raw data you get from the Crystal 16. If you look at the red line, that's showing the temperature. So at the very beginning, it goes up, that's because we're heating these vials up, and then it drops down to -10 degrees, and then it holds at -10 degrees for a long time. So the other lines you're seeing, the blue and the green lines, those are samples, and we see those lines go up and kind of be up at the top, and that's because they're dissolved. And then when you see the drop off, that is when they are precipitating and crashing out of solution. So what was odd about this is these three samples are identical. They're the same concentration. They're also extremely concentrated. They're at almost 2 times the concentration of what the room temperature solubility was. But despite that, even going all the way down to -10 degrees, we still didn't get crystallization as we were cooling, which is what we need in order to define our metastable zone with. Instead, what we saw was a more heterogeneous nucleation. So all of these sort of just crashed out at random times when it started crystallizing on the sides of the vials. So to kind of go back to our definition of metastable zone with, what we think is happening here is we start with our saturated samples at different, or in this case, they're the same concentrations, but we would have different concentrations. We heat them up past the solubility curve, so they should all be dissolved in solution. We then take those dissolved samples, we cool them back down, and we should be hitting that metastable limit at some point and see cloudiness and see precipitation start. But we never get low enough in temperature to hit that. So instead, we're remaining in that metastable, unstable region, and we just have a random nucleation occur. And that's why all these nucleations are sort of occurring at different times, and we're not really able to control the timing for these nucleations. So there were other systems we were able to find the metastable limit curve, but it was extremely low in temperature and had just a very, very wide metastable width. So this data here is the the resulting data you get from the crystal 16 when you're generating a metastable zone with. So on the right side, we have all those points that are different concentrations, clear points, and that line is defining our solubility curve. And then on the left, we have all of our cloud points, those concentrations defining our metastable limit. I know it's really small, I apologize for that, but all of those points are below 0 degrees Celsius. So because this is such a large gap in the metastable zone width, we have a very large unstable region. It also requires our samples to be very concentrated. These are all 40 meg per mil or higher in order to even get to this point. So this system, although we were happy to finally start getting some data, it probably took us 20 or so tries, which is not normal when we're doing these types of experiments. We were able to finally get some data, which was exciting. And then this is showing our system that had our top result from our initial screening. So this is our DME heptane system. This is still sort of a large metastable zone width, but at least that metastable limit curve, that blue line, you can see it is a little bit steeper and it's at some more reasonable temperatures. It's at 25 degrees or so, where we're able to start crashing out our samples. We still are requiring a pretty high saturation for these. So these are all around 30 meg per mil or higher, but at least at those higher concentrations, we're able to have less of a metastable zone width gap, and we're able to sort of control where we get the nucleation at a reasonable temperature. So because this was our most reliable system, we wanted to evaluate this a little bit more, see if it was repeatable, and confirm if we're able to control the morphology that we wanted. So this metastable curve here is just showing a bunch more sample runs of the same system. We wanted to show that it was repeatable, which it appeared to be repeatable, which was great. I also have circled there that one cluster of data points. Essentially what this is the same sample that we cycled multiple times at different cooling rates, because we wanted to see if there's any sort of variation in the results if we did that. We found that regardless of the cooling rate, we did still crash out. We did still get our needles, and we still got low void solvent from all of these. But the faster the cooling rate, we actually got better results. We had less solvent in the lattice, and we also had they crashed out quicker at a higher temperature. So we sort of resulted from that. The faster you cool it down, the better the result will be. And the slower you do, sometimes the results are a little less than ideal. But overall, these samples looked great. We have our long, thin needles, and we have a very low void solvent from all of these. We're able to show repeatability that we can control for this morphology as well with this system. So in conclusion, this project had powder properties and macroscopic morphology of a compound X that we found was influenced by the amount of solvent trapped within the lattice, which interrupted the growth pattern and resulted in radially divergent growth clusters. This void solvent is not going to be removed by drying or micronization or any sort of mechanical stress because it's trapped in the lattice. So you can only remove it when you break down the lattice by melting it. We also were able to find through crystallization control that if we use larger volume solvents, we were repeatedly able to achieve low void solvent in our particles and a needle-like morphology. And if we crystallize with these smaller volume solvents, we were able to achieve the high void solvent with the clustering particles. We also found that overall a faster cooling rate and having a very high supersaturation yielded better results. And just some acknowledgements. I want to thank my team and some other colleagues and coworkers from Neurocrine who assisted in this project. And of course, Technovus, thank you so much for having me. And that is all. Thank you.
Thank you very much, Christina. Really interesting and a very nice case study that actually you have shared with us. I imagine trying to get to the bottom of it was not the easiest thing ever.
Not quite, but it was fun.
Indeed. Thank you very much. We have a few questions, but just before I start, as I understand it right, how is your workflow around the Crystal 16? So you get a compound, you do a solubility study, am I right? And then you start to design your experiments depending on whatever you find out in the first studies, right?
Yeah, it depends on the project and where it's at and the challenges associated with that project.
Exactly.
So sometimes we already know what the solvent system is going to be because it's already, been determined by the synthesis and the chemical development folks. So sometimes we already know what to work with and we're just tweaking ratios or better understanding and defining the metastable zone with. Other times like this, where it's sort of a special case where we're doing a more broad design of experiment.
Okay, thank you. We do have a few questions because you had quite a few nice pictures from microscopy. One of our attendees is asking, is the needle morphology not a problem for filtration? You had also
it could be. Yeah, so I don't really come to any conclusions on which morphology we want or we're going to move forward with necessarily. This was more so to figure out which one we want versus the other. Both have pros and cons. Of course, needle-like morphology sometimes is a challenge, but there's always micronization and other tools you can use to control once you have that. But the problem is with the void solvent clusters, you can still micronize them, but you're not going to get rid of the void solvent. So,
yeah. Alice is asking, have you found any similar published studies where a new polymorphic form was found with a void solvent?
I don't think I have. I did do a little bit of research to see if anybody had similar studies to this one. I mean, you can absolutely have polymorphic forms of your compound that will or will not have void solvent. We were very confident with the polymorph on this one. We checked it every time still, but yeah, the polymorph itself is very solid in this case. So we weren't really worried about it forming a solvate. It was more just whether or not it was getting trapped in the lattice or not. But it actually does also have solvates with different solvents, but we didn't choose those solvent systems in the study.
Yeah, and because you are now mentioning about the solvent systems, another attendee is asking, could you please provide a few hints, suggestions on how to seed and avoid aggregation?
Yeah, I think that's this is an unfortunate answer, but it's very dependent on the molecule. It's hard to have a case that's going to, solve everything. I think what I would do in that case if I was seeing aggregation, having trouble controlling for that in the crystallization, is choose a range of polarity in your solvents. We might have a case where maybe if you have something that's a little hydrophobic and it likes to stick to itself and maybe it's agglomerating that way. If you have a different polarity solvent, maybe you're more likely to break those up. There's also, you typically use like surfactants and things when you're using crystallization. But if it was a big problem, you could potentially investigate using something like that.
Indeed. What happens in a non-seeded trial at similar supersaturation ratio?
A non-seed. So all of those trials were all non-seeded. So everything at the end, when we were looking at binary mixtures, none of those were seeded. We did do some experiments with seeding as well in some of the solvent systems, and we found that it was difficult to control, which is strange because usually seeding helps you control your particle size, but really, seeding is essential if you're trying to control for a polymorphic form as well, because you introduce that seed and then you encourage growth of that same polymorph. In this case, we're not worried about that at all. The polymorph grows just fine. What's happening here is the actual triggering of that nucleation and growth is what's causing these to sort of fuse and grow on top of each other. So whether or not we have the seeds or not, that didn't seem to necessarily make a difference to the end of the morphology. It did help to control the time and the rate and how quickly we were able to nucleate.
Yes.
But otherwise, yeah, we didn't see seeding as a way to necessarily control for the morphology.
Do you have issues with cold spots or condensation with your TGA-MS, with the TGMS? If so, do you have any recommendations on how to prevent this?
We don't currently. So our TGMS is through TA instruments, and we have the accessory that comes with it with them. So it's all kind of built in as one unit. So it works pretty well for us.
Okay. Have you tried milling your material to break up the clusters to release the void solvent? If so, did it work?
Yes, we did do studies, various studies with micronization and grinding with some of the larger void solvent particles to try to break it up. We found that it lowered it a little bit, but not significantly. So for instance, from like 1.2 to 0.9. So it did lower it a little bit, but you're breaking up some of it. So you are releasing some of the voids and breaking some of those up, but so much of it is still integrated into the actual lattice that you're not able to completely remove it with grinding.
Yeah. And another question, how to remove trapped residual solvent from amorphous solid?
So if you have residual solvent, that's a little different. So there's different types of solvates, so everything kind of depends on what you have going on. So if you have something that's just residual solvent where it's just sitting on top of your materials, just sort of wedded to the material, usually just a good vacuum dry will get rid of that. So you want to understand the thermodynamics of your material first. You'll want to know, where your glass transition is and everything, if it's amorphous, or your melt if it's crystalline. So you make sure you don't heat up and dry past that point and interrupt the structure at all. But if it's just residual that's sitting on your material, you should be able to vacuum dry up to a certain point and remove most of that. You could do different time trials to see the percentage that is removed during certain times and sort of decide if you need, 30 minutes, an hour, a day, and sort of what's the most reliable way to dry the material. A little trickier example is if you have something like a channel solvate. So void solvates, you can think of them like little pockets within the lattice. A channel solvate is more like a tunnel that goes all the way through. And a lot of the times you'll see channel solvates with something like water, where it picks it up just from the air, and those little water molecules will go into the channel and just sit there at a certain humidity. And really all you can do to control for that is humidity control. So using drying agents when you're packaging and that kind of thing.
Thank you very much, Christina. It's we are now online almost 1 hour. I did have a few more questions. Okay, let's try one more. Did you obtain X-ray crystal structures to see the actual void spaces? Thanks, Mike.
Yes, we did. We did do single crystal X-ray determination, and we didn't do calculations to actually determine the volume, but I chatted with the crystallographer and we confirmed that the spaces that were in the lattice packing were large enough to trap various size volume solvents.
Is there a correlation between the degree of crystallinity and the morphology in your samples?
It's a good question. We didn't do a full assessment of degree of crystallinity, but pretty much across the board, all of these samples were extremely crystalline. We didn't see much variation. We didn't see a lot of decrease in ripeness or anything like that when we were looking at the particles. So we didn't really determine that to be a major point of consideration. So we didn't look into it any further. But it's definitely something that could have affected it for sure.
Yeah. Last question. This is really the last one. Did you try thermocycling to avoid solvent entrapping? Indeed, I do remember a long time ago, we were also doing a lot of thermocycling to try to get rid of those solvents.
Yeah, we did do a few studies with that. I guess the problem there was we were ideally trying to find a way to control the morphology that lowered the time required for the crystallization. So we didn't want to do something where we had to have a lot of cycles, because we just wanted one nice, clean cooling run that resulted in what we wanted.
Yeah. Okay. Thank you very much, Christina. Thank you all for sharing all your thoughts and questions with Christina. I think now we really answered everyone. Oh no, they are still coming, a few more. I will send them to you.
You can send them to me.
Email, yes, to answer directly. Thank you all. The recording will be available on our website as usual, and also the slides to be able to download them. If you have further questions to Christina, you can write to us, and we make sure that she receives all the information from us. Thank you again. Have a good day, good afternoon, good evening, and we see you in a month or so on our next webinar. Thank you all. Thank you, Christina.
Thank you.